So I say, yeah, welcome to this new webinar. It's organized by the expert group dealing with geological mapping and modeling, belonging to the EuroGeoSurveys. And today the topic regards geological modeling using some new capabilities that are integrated to QGIS. That is one of the most used GIS in the world. These developments are conducted in the 3D team of BRGM, the French Geological Survey. And we are happy today to welcome Nicolas Clauzol. Nicolas is a colleague of mine at BRGM since almost 5 years now. Nicolas is graduated from the Geology School of Nancy in France. He is a specialist in 3D geomodeling, both for construction of models and also for the development of solutions. So talking about solutions, Nicolas is going to present us the work that is ongoing at BRGM to propose new features, new capacities of 3D geomodeling within QGIS, the GIS that you all know, I presume, or you heard about it at least. So Nicolas, please, the floor is yours.
Thank you, Philippe. So hi, everyone. Once again, yeah, thank you very much for being so numerous today. It's quite a nice audience that we have. As Philippe said, I'm going to present you the work we've been doing to implement the tool, namely ForGEO, for doing 3D geological modeling in QGIS at BRGM. So to give you a bit of context and background, we've been building 3D geological models at BRGM for decades, and for various purposes, for geological knowledge, as well as we produce geological maps. We also build geological models to get a better understanding of the subsurface, but also for the needs of various downstream predictive applications.
BRGM's utveckling.
To do that, we've been using a large variety of softwares. So commercial softwares like SquagoCAD, Petrel, Isatis, Serpa, Leapfrog, and probably many others. But we also have a specificity at BRGM, which is that we have been developing our homemade tools since almost the beginning in the 80s. So we had two historical tools, namely GDM and GeoModeler, who implement two different modeling methods. And alongside that, we also had many standalone and one-shot developments that were meant to answer the very specific need of some projects or another. So in this context, why do we need a new tool? First, our homemade software that was the one that we mainly used in most of our projects, are, let's say, softwares from the 20th century thought as monolithic software who should do everything at one place. And over the years, this monolithic software has accumulated quite a lot of technical debt, which made them hard to evolve and to maintain. And an important point is that we need to have a control over our production tools because, well, first they implement our know-how, but our production tools are also the repository for our research and development works. And as I said, we often have to develop some specific solutions dedicated to one single project. And in order to do so, one prerequisite is that we have to have the control over our tools. Another point is that we are facing nowadays demands for increasingly complex models in terms of quantity of data, of diversity of data, of scales and ranges of scales to model. And our historical software starts to reach the limits to answer these problems. So that motivated the work I will be presenting. And one important point is that if we compare the situation where when we started the development a few years ago, to the situation where our historical tools were born, the context has changed quite a lot. First, we have been facing over years an accumulation of the number of tools, numerical tools, and software we have been using at BRGM. It starts to be a problem to handle all this large collection of tools. And we have, there is an internal trend, let's say at BRGM, which is to try to reduce the amount of software we use in our production workflows. And another aspect is that we try to rationalize costs that are related to the operation of these tools, should it be, for example, licenses or also the infrastructure to operate these tools. So within this line, there is currently a move at BRGM toward having a finite set of digital platforms. So we have quite a lot. We have several projects which aim at setting up web-based or cloud-based platform, either for our internal use or at BRGM or for, let's say, more academic uses, so open to the French research community. But there are not only web-based digital platform. We can think some desktop softwares as platforms too, and this will be an important part of what I will be presenting today about QGIS. So that's for what happens at BRGM, but if we look a bit outside, what we can see is that the legislative and institutional framework is evolving a lot since a few decades. In France, since 2016, there is a law that states that any data, code included, which is produced on public fundings, should be open and accessible. And if we look at the EU scale, even though the 2019 directive on open data and public, on open data, let's say, did not include computer programs into what should be open and accessible, there has been several versions of the open source software strategies, and the new updated version is about to arrive later this year. Another point we can mention also in this line is that there are also some related actions within European project and especially GSEU, as we have a task dedicated to sharing methods about open tools, workflows, and best practices in 3D modeling and visualization. So what is new as compared as a few decades ago is that there is really this move toward open source software. So that's the motivation that made us going toward QGIS. And the first question is why integrating 3D modeling into a GIS? The first thing is that GIS software has become the central tool for managing and processing georeference data. Almost all domains of geoscience use nowadays a GIS software for managing data. And one of the great advantages it has is that it proposes seamless connections to databases and web services. So that's really a tool everyone is already using, or almost everyone. And that's why we wanted to integrate 3D modeling into a GIS software and not to redevelop a software on its own, as it was before. Now, why QGIS? Well, and especially as compared to ArcGIS, the first thing is that it's open source and free to operate. It has an extremely vibrant community. I have to thank Chris for this illustration, but if we compare the situation, I said the image is just an illustration of Google Trends Analytics comparing ArcGIS versus QGIS. But 10 years ago, in 2015, we can see that ArcGIS was largely predominant almost everywhere in the world. And 10 years later, we see that QGIS has grown quite a lot. So now it has a very vibrant community, but another extremely powerful capacity of QGIS is that it's extremely it's really easy to extend it through its mechanisms of plugins. So that's what we have been using in ForGEO, but there are so many other examples of QGIS plugins that many of you probably already used in the community. So it's really easy to add new functionalities to QGIS thanks to these plugins. Another interesting point is that QGIS is constantly evolving, including for everything which is related to 3D. It now handles 3D coordinate reference systems. Since a few years, it's providing a 3D visualization tool. It allows to draw cross sections, to have vertical 2D views. But the thing is that it's evolving a bit slowly. We'll have the occasion to talk about that later. Now, the good news is that QGIS 4 is coming out tomorrow. And that's quite a major release, not especially from a user point of view, but for developers and for the maintenance of the code. It's a very important release. So we'll probably soon have quite a lot of new, quite exciting functionalities coming with it. So we make the choice to integrate our development in QGIS. And now speaking a bit more about this development, what is ForGEO? Well, ForGEO is a plugin to do structural and stratigraphic modeling into QGIS. In order to give you a brief overview, we are talking about stratigraphic and structural modeling. A bit more specifically, we are talking about 3D implicit modeling, so which has become quite the norm these last 2 decades in terms of 3D modeling for geology. It's similar to what can implement tools like GeoModeler, Petrel, Square, or Leapfrog. And in terms of modeling, we are talking about modeling stratigraphic deposits, so which have let's say a layered behavior and intrusions. And these deposits and intrusions are affected by structural events, so quite typically folding or faulting. One of the big points, let's say, in ForGEO is that, as I said previously, we had 2 different modeling tools originally that implemented 2 different modeling approaches. And a very important focus of ForGEO is to manage to combine these 2 methods into one single tool, and more specifically into one single model. So we have been putting quite a lot of efforts in order to be able to combine various modeling approaches into one single geomodel, because depending on the data you have for your different modeling elements, not all methods are as relevant as one another. And the second focus we had when we're developing this is that we want to orient it or to get it ready for quantitative applications. So typically for whatever you could expect, like hydrogeology, geophysics, or whatever. And we are putting quite a lot of efforts also on everything which is related to discretizations, which is so extracting surfaces and meshes that are conformable to all the different surfaces in order to make ready for physical simulators downstream. Now, if we dig a bit more into the details, there are 3 main components that will make up GeoModel in ForGEO, and it's pretty classical in terms of geomodeling. We will define a geological pile, or how to say that? You can, well, use that in any other modeler, should it be called a geologic pile or stratigraphic column. The idea of this pile is that you will define the main elements to model in terms of geological unit and interfaces, and you will define the overall global architecture of these rock volumes. The second element will be the structural network. So you will define the different fault surfaces that can affect the stratigraphy and their geometry and how they interact between each other. So basically the branching rules. And the final element is the stratigraphic model, which will control the fine scale architecture of the deposits. And that will make the link between these deposits and the fault network. So if we zoom in a bit on each of these elements, the first, the geologic pile, as I said, the idea is to define all the modeling units that will be present in the model. You can think about it exactly as what would be the legend of a geological map. It will also define the different stratigraphic interfaces that are present between these units and how all these elements are organized. So basically, it will describe the depositional logic that has been in place between the different elements. So is it only, let's say, a mere piling up of sediments, in which case it will be unlapping structures, or did at some point we had some matter removed, and in this case we will integrate erosions or unconformities. If we look at a bit at what it looks like into QGIS, so here is a project I will be using to illustrate everything that I will be presenting. We are located south of France. Let's say that it's a toy model. All data come from field mapping campaign that master students are doing as part of their university courses. So we are somewhere between Roche-Sadoul and Foussignargues. And the idea is that, okay, we have some field data, so mainly orientation measurements and surface or unit observation that have been collected on the fields, and we will want to build 3D models out of that. So I was talking about the stratigraphic column. Here it is. As I said, it's very basic. It just defines the different units you will be modeling. So here you can see that we are quite large scale in terms of geological times. And here it is. So that's the first point. The next point is, coming back to the presentation, the stratigraphic model. Once we have defined all the elements that will be part of that our model, we will start to look at a bit more into the details. So the first thing is that we will have to convert, let's say, geological concepts into geometric rules. And especially what we will have to do is to try to interpret geological depositional relationships, so for example on labs, etc., into what will be interpreted by the computer as 3D surface truncations, so something that has nothing to do anymore with geology. This fine scale tuning of the geology will define different ensembles that will be interpolated together afterward. I won't dive into much details, but I was talking about implicit modeling methods a bit sooner. And the idea of implicit modeling is that you can model a series of subparallel surfaces all together. And so this fine tuning that you will of the geometry that you will select here will define the different stratigraphic ensemble that you will interpolate by the end. The next big step is we will have to assign data to each of the different elements to model. Excuse me. We will have then, once you have assigned data, you will have to define some interpolation parameters. So it's a more mathematical step. And finally, you will have to define which discontinuities affect the stratigraphy. And so for each of the stratigraphic ensemble you will be modeling, basically which fault affect them. If we come back to QGIS, what it looks like is that once you have defined your stratigraphic column, so as I was saying, you will be defining the fine scale geometry of your strata. So basically, you will say, okay, for each contact between units, is it parallel to the stratigraphy of the lower and upper units or not? And it will define the different interpolation blocks. For the data assignment, I can present you a bit the data before. I told you that these were mostly data collected on the field. So everything is, or most of it is stored into a vector layer, a point layer. Each line, each feature in this layer corresponds to one data point. It's quite a messy file, but the idea is that the data have been collected using QField. For, if you know this tool, it's a QGIS plugin that allows you to have a very light QGIS version on your smartphone or tablet. So all the data have been collected on the field in QField, and this quite complex setup is made in order to have the data already ready to be capitalized in our internal databases at BRGM afterward. For what will interest us, let's say that for each data point, should it be an observation or an orientation measurements, we will have in this column to which element it refers to, or the interpretation of what it's supposed to be assigned to. And for some of them, we will have also deep direction measurements. So that's our base data. And when you will assign data here for a surface or a unit in your geological model, what you will say is that, okay, you will find data for this element in the three different QGIS layers. So point observation is the one we're looking at, and there are also two others. And for each of these three layers, you will look at the values which are located in the field named litho comment, so the one I was showing here. And in this field, you will filter all the values which are either layers, trias layers, or etc. So basically what you are doing here is just defining a quite simple filter over one of your data source in QGIS. So it will automatically extract all the points that you listed here or you defined here. And what you can say additionally is that if you have orientation measurements, you will say, okay, the column of my data source that contains the deep measurements is named deep 1. That was the one I was pointing at here. And the column that contains, I should not have closed, okay, here, the deep direction is here. So basically, it's just parameterizing one filter per layer in which you have data for the given element. So that's for the data assignment. The next step is to parameterize interpolator. As I said, we put quite a lot of efforts into merging or combining two different interpolation methods into ForGEO. That's where it happens. You can either choose to interpolate using the potential field method or a 2D kriging of the elevation. So for each case, you will have to define some interpolation parameters. These are both methods based on a geostatistical framework. So basically, the parameters you will find here and here are just geostatistical parameters. That's it. Last point, again, is that you will select the fault. I will present them just after. That will affect each of the stratigraphic series in your model. So here we have parameterized everything for the stratigraphic model. The last step is, coming back to the presentation, is to define the structural network. And it will be exactly the same idea of the two previous elements, the geologic pile and the stratigraphic model. It's just that here, both steps are combined together. You will first define each fault that may affect the stratigraphy. You will have the choice for each fault later to choose if it affects, if you want to integrate it or not. You define their geometric properties. So basically you parameterize interpolation. And you define branching rules between each fault to define which faults stop on which other one. So that's a very broad idea. I won't dive into much details because it's exactly the same that you will retrieve here. So, so far, what we have been discussing together is literally a 3D geomodeling engine to build 3D structural models in QGIS. Now, there are quite a lot of topics that we have not mentioned, but that we know are, let's say, of major interest when you build a 3D model. For example, we have not covered visualization, either 2D or 3D. We have not told about geostatistics, except that you have to enter some parameters. And there are many other aspects like geophysics, for example, that we've not mentioned. Now, the thing is that we have to keep in mind that all these different topics are not, strictly speaking, dependent of the 3D geological modeling engine. These are related needs, but you may need visualization or geostatistics capabilities, even though you're not building a 3D model. And that's why there is this idea of trying to move toward an ecosystem of QGIS plugins for geosciences. So before I was presenting ForGEO, which is for interpolating, let's say, 3D models. But we have put quite a lot of efforts into developing a collection of side plugins that helps with various other related aspects of subsurface studies, let's say, for QGIS. The first one is PVGIS, which is a plugin for 3D visualization into QGIS. It's based on VDK, a very common 3D modeling, 3D visualization engine in the scientific community. And the idea is to have a QGIS plugin that is able to visualize in 3D any kind of common GIS layers, so vector layers, raster layers, but also 3D meshed objects. So especially for us in order to visualize the 3D models, but we can also think about boreholes, for example. It also permits to visualize object properties. So here is an example here of 3D gravity anomaly map. It can drape images, etc. The idea is to have a light tool in order to visualize 3D data into QGIS. And as I was speaking, so just to give you an example of our 3D model, we may want to, once our model is parameterized, we may want to evaluate it. And so, for example, let's try to compute it we open the 3D visualizer, and here we have the result of our computation. So it's pretty basic. Oh, I already had an example. Nice. It's pretty basic, but it allows you to visualize the different surfaces that have been extracted, to hide faults, to hide formations, etc. You can also send to this tool, as I said, any kind of GIS layers, and that's it. A last interesting point with this tool is that as we often need to share our 3D models with clients or with colleagues, this 3D visualization plugin also works as a standalone application outside QGIS, and you can save the state of the viewer at some point, so you can prepare 3D scenes that you redistribute to your colleagues, etc. So that's for 3D visualization, but even without talking about 3D, another core requirement for geologists is to be able to see cross sections, to visualize, edit, etc. Data in cross sections. For that, QGIS recently integrated a tool, a former plugin that is called the elevation profile. So you can visualize data along vertical cross section in QGIS. But the thing is that you cannot natively visualize, for example, images. And that's quite a common need for us. Should it be an interpretative geological cross-section? Should it be geophysical profiles? You want to be able to visualize 3D images within this elevation profile. So for that, we've been collaborating with a French company, which is called Oslandia, and which is specialized in the development of QGIS and QGIS plugins, in order to propose a plugin called Woody, whose work is to georeference images along 2D lines, but vertically, and to allow to visualize them in the cross profile. One important point about this work is that I've been saying in the introduction that QGIS is evolving towards 3D, but it's evolving quite slowly, and it's not necessarily evolving the way we need it to evolve. When I say we, it's we people dealing with subsurface data. Because quite a lot of 3D actually in QGIS is about, for example, LiDAR acquisition of point sets. And that's where we start, our BRGM development team about 3D started to get involved into the development of the QGIS source code. We've been doing that for 1 year now, approximately. And the first point was just to be able to draw whatever, to allow plugin to draw, let's say, whatever they want in the elevation profiles. And typically, in order for Woody to be able to draw images, we had to push some minor modifications, which are already available in the current QGIS release. And the very new point, and we are pretty happy about that, is that we've been pushing, let's say, more complex development in order to be able to digitize data within the elevation profiles. So for example, for digitizing or interpreting cross sections and seismic profiles. And it's finally accepted, and it will soon be released with QGIS 4.2 in June. So coming back to Woody, if we look at it in QGIS, so the idea is that you can open the elevation profile here. I already georeferenced to in some time a cross section and I lost it. Oh no, here it is. Okay. I just have to show it on the map. Okay, so I georeference an image here, and if I ask the elevation profile to draw the image here, I have to rescale it. Okay, I probably changed something in the parameterization of my cross sections. Let's say that this one is not really demonstrated. But the idea is that thanks to Woody, you can load an image and georeference 2 points on it in order to replace it properly in 3D, or in 3D, in the elevation profile.
Nicolas, I think it's time to come to the conclusion. Yeah,
okay.
to have time for discussion and question. Thank you.
Okay, excuse me, Philip. So coming back very quickly, alongside this visualization needs, we have also developed a plugin for doing some basic geostatistical analysis, so computing variograms and doing rigging. We plan to complete it with cross-validations and simulations by the end of the year. And we've been working with geophysics. I'm pretty late. So I will go quite quickly into the on it, but the idea is to be able to move toward forward and inverse modeling for various geophysical applications. So the first thing we've been working on is gravity modeling. We have also quite a lot of other colleagues at BRGM working on QGIS plugins. So here is an example from the geophysics team for a plugin manipulating and editing geophysical data with airborne aeromagnetics and 3D resistivity cube. And to conclude, but there are, well, no, just to mention also, that's one example of works outside of our team at BRGM, but you have many others. For those involved in GSEU, you've seen probably the tool for data lithostratigraphic and lithotectonic unit data assignments developed by Maxime Padel and Isabelle Bernachot. We have tools for hydrogeology, for any kinds of applications, basically. So to conclude, because I'm late, sorry. ForGEO is a 3D geological modeling engine that allows to build multi-purpose 3D geological models directly into QGIS. So it implements a pretty classical modeling workflow. You just have to define your stratigraphic column, fault network, and a stratigraphic model. There is an important focus on the 3D models to be fitted for downstream quantitative application. So we've been working quite a lot on meshing, gridding, etc. And it's not yet finished. If you want to get started, the first point is that, as I said, we are pushing modifications directly into QGIS core code. So you need a pretty recent QGIS version. The documentation is available online. And if you want to install it, you will retrieve through the QGIS plugin manager. You just have to look for BRGM and you will find all the list of plugins I've been presented. The documentation is available through the homepage link, so you don't have to remind this one. Just a small disclaimer, that's work in progress. We are working pretty hard on it, so it will also evolve quite a lot within the next year or years. So yeah, do not hesitate to keep up to date. And that was for ForGEO, but another very important aspect is that, okay, it's a 3D modeling engine, but it's integrated into QGIS. And we really want to try to move toward having QGIS as the daily tool for any geoscientist dealing with subsurface data. It's open source, it has a very vibrant community, already also from people from geosciences. It's highly extensible. So yeah, we should really go for it. It's evolving towards 3D. The only requirement is that we, subsurface geoscientists, have to become active members of its community if we want it to move in the direction that we want. And we also need a place to discuss all these points, and that's where we are really happy to have projects like GSEU for having such discussion places. That's what I mentioned earlier in the video, in the presentation. Yeah. Thank you for your attention.
Thank you, Nicolas. Thank you for this comprehensive presentation and demonstration as well of ForGEO and much more within QGIS. So you have been listened by more than 230 people. It's quite impressive. Yeah, it's good. So let's now move. We still have about 15 minutes. Let's move to questions and comments. So if you have any question, please raise your hand. I think it will be possible to open to open your microphone. But we have already some question in the chat. So the first one is about the recording. Yes, you have seen that maybe in the chat. The webinar is recorded and will be available on the EGS EuroGeoSurveys YouTube channel. So Irena put the link in the chat, so you can have a look on the previous webinars already. So first question. The question is about how do you model intrusion? So a specific type of geological object, like a dike, or they appear in this methodology.
I try to come back to the slide to get a visual
maybe quite short answers as well, because we have
the idea
already
is
a lot of questions in the chat. Yeah.
In what I've been presenting, I've been mainly talking about stratigraphic modeling and layered sediments, but from a mathematical point of view, interpolation point of view, or software point of view, all this is really about 3D surface truncation rules. So what you will have to do is to place at some, well, to include your intrusion somewhere in your geological timeline. And in fact, much like erosions, for example, the idea is that an intrusion can affect everything which is older than it. So you will just have to. So how to say that? You could define it as an unconformity, and it should work then. If you define it as an erosion, the surface above the intrusion. But that's, let's say that we are planning probably within the next year to have a specific object for users for that, in order not to have to think about that.
Okay, this was a question from Magali. Now we have a question from Anton. Is there any available dataset already prepared as a tutorial for what you have shown?
No, that's one of the big points. That's what I was saying at the end. We are currently working quite a lot on it. We have been training our first users at BRGM. People are currently starting to use it in some projects. So there is a major effort of documentation and tutorials that we're currently doing, and I think by June or July, that will be ready. You already have some documentation about how to use it, but not the dataset.
Okay, next question from Roland about the monolithic tools you were talking about in the introduction, especially GDM and GeoModeler. The question is, isn't there a risk to build another monolithic piece of software here within QGIS?
One might see QGIS as a monolithic software. It's probably quite true. But the good news is that the community around QGIS that maintain it is much larger than the community we might have or we could have in terms of human resources at BRGM to maintain ForGEO and GDM. So even though it's quite monolithic, there are much more persons, people working on maintaining it. So that was for the monolithic aspect. And was there another point that I missed, or?
No, I think it was about this monolithic issue, and maybe as a complement, we can say that what is developed here is plugged on QGIS, but the plugins are also will be also used for other software or platform or whatever. Of course, we need the interface with such a platform, but all the bricks that are developed here could be and can be used in some other context as well.
Yeah, and maybe a final comment on it, thinking afterward. There is obviously some kind of risk about becoming monolithic again, but that's why I insisted on saying that, okay, ForGEO is a core modeling engine. So it's about interpolation purposes. And all related needs, 3D visualization, geostatistical analysis, 2D visualization or whatever, integrating geophysical capacities are separate plugins. They have to be able to live independently.
Okay, thank you. And the next question is about the demo you displayed regarding the size of the study area. So it was quite small at the scale of the French territory, for instance. And the comment and the question is about if you deal with a larger area, is it more difficult? And for example, if you have a unit that is present appears in a part of this area, but not in another one, or can be taken into account, and the same for erosional surface that could be erosional on a part of the area, but not on another part. So there was a multiple question, I think, in that one. The first one about the size of the study and the fact that you don't necessarily have the geological formation everywhere in the study.
That's an excellent question. Let's say it's not related to ForGEO, it's much more general. It's the problem that any structural and stratigraphic modeling software are facing, because when you say, or in these approaches, you assume that you do not have lateral facies variations. So how can you deal with that? You can imagine several things. First is having a multi-layered approach, a multi-scale approach. You will define first large blocks by grouping several different units all together, even though you want to keep them separate in the end. And once you have these different blocks, you can try to model more finely within each, let's say, mega unit, the variations with them. So you decorrelate the surface truncation rules at large scale and at small scales. That can be an approach. But yeah, I would say any 3D stratigraphic modeler will have difficulties for that.
Yeah, it's a general question, but we need to keep in mind that the modeling of the formation are driven by the data. So the fact that a formation will appear in a part and not in another one will be driven by the data. So it's the way it works. And the second part of the question was about a different behavior of an erosional of a surface towards the others. For instance, erosional on one part and not on the other part. So in that case, it's quite more tricky because you certainly need to define two parts, two different areas with different relationship in your study area. But it's on the list as well of what is developed here. A technical question regarding format, which is the format of model surfaces, grids or unstructured meshes?
For now, we are mainly manipulating VTK formats because the first need is to send them toward, to send them to the visualization tool. That's a point that will come with time and with uses. We will be enriching the different formats we can generate with the needs of our users.
Yep.
I guess.
And then formats associated to QGIS, I presume, as well.
Yeah, but then you have the difficulty that QGIS does not define all kind of 3D formats, like meshes you cannot, or 3D meshes.
A question about Woody. This plugin work on multi-segment or not straight polylines?
Not yet. And that's where I was saying that it would be great to have a larger community of subsurface modelers to support actions toward it. In the first version of Woody, you can only manipulate one segment line. We are planning to work with Oslandia again for the, let's say, the next version that will include polylines, but yeah, it's not yet available, probably by the end of the year. But we need it for all kinds of geophysical sections, etc. So should come. But we would be happy to share the cost too at some point.
Another question about 3D voxel model XYZ, for instance, coming from geophysics, geophysical data, and isosurfaces of selected values from it be constructed and displayed in 3D using GeoGIS. I don't know if you know this one.
I can't answer this one, unfortunately. I will transfer it to my colleague.
Yeah. It's a question from Lyell. If you want to maybe to add more detail or on your question, because it's possible to visualize a 3D voxel model XYZ in what you have shown. Is it Nicolas to visualize a grid XYZ?
I don't know if it's readily available.
Okay.
It would not be well, it's probably, I won't speak for GeoPhysics, but for PVGIS, I don't know if it can, but it would be easy. The only question is to read the input format, but it's not really hard. So one might clone the source code and implement its own parser in PVGIS.
Okay. A question about maybe more strategy and are you aiming to move away from 3D existing modeling software such as Petrel, GoCAD, Leapfrog, and so on? Or do you think you will still need them?
A disclaimer, this will be my answer. I'm not the one designing such points at BRGM, obviously. I'm just a technical staff. I don't think we will completely move away from other modeling software. I guess the main point is to come back to the previous situation with our, let's say, former modeling softwares, where we had two internal modeling softwares that we knew really well, where we had very expert users, and that were suited to answer most, but not all of our needs. And for all other situations, so when our tools do not have the capacities for, or when some client requires that the model should be done with some given software, in these cases, we will continue to use external tools too. So,
yep. And maybe here a complement, if BRGM decided to of course invest in such a way, that means that this development become a kind of enterprise initiative. So for sure we will do as much as we can in this kind of environment to reach what we need to do in our projects. Something about exports, we a bit discussed about that. How the resulting model can be exported from QGIS. I presume in 3D or not.
Yeah.
We discussed about surfaces. Yeah.
We discussed about surfaces because for now we only have surface exports. 3D volume export is about to come. We will be working on it during the spring and summer. So by September, we should have a 3D modeling export. I guess in the first time, we will stick to some pretty common format, probably VTK, and then it's just a question of implementing converters. You have quite a lot of available Python libraries that do such things that are already available. So yeah.
Yeah. Okay, a question about input data and especially seismic data, 2D or 3D. So about 3D, we already had this discussion about the 3D grid. About 2D, it's of course possible to input 2D grids or even images as you have shown in the demo.
Excuse me?
For seismic data, it's possible to input the information as 2D grids, I presume, in the sections, for instance.
It should be now. Well, it's somehow pretty limited for now. The elevation, what we have implemented in the elevation profile is reading image files, so PNG, TIFF, etc. So either you load that or loading Segway files or other specific formats is still to be implemented. We will probably not do that on our own, or at least that's clearly not on the list of priorities. But that's where, once again, there is this idea of having a community. One people or one group do the implementation and share it with the rest of the community. So if people want to start to get or to add plugins for displaying segues in the elevation profile, that would be great, definitely.
Okay, this is also the advantage of such a community and the capability of developing open source plugins. Yeah, I think it's time to conclude. It's a bit more than 3 o'clock. I think we have answered almost all the question in the chat. I see that Leana answered some of them, so I think we can conclude here. So thank you again, Nicolas, and to all of you for your participation to this webinar. And let's see you for the next one, the next webinar. Bye-bye.